day, dear students. As we have discussed last class, we have solved many good numericals related to steady flow energy equation. We have seen the application of first law of thermodynamics to SFE, and we have solved a handsome amount of good problems concerned with SFE application. So in this lecture today, we are going to discuss the second law of thermodynamics, which is of more practical importance as compared to that of the first law. So in second law of thermodynamics, I am going to just brief that what are the keystones that you need to study. So you will be going through study the thermal source or a source of a heat and a heat sink. So what is basically a heat sink, thermodynamics definition, and what is the heat source, the definition of thermodynamics. Then you are going to investigate a heat engine using Carnot cycle. You are going to evaluate its efficiency, and then we are also going to see what happens when you reverse the heat engine. So when you are reversing the heat engine, it is becoming a refrigerator. So you are going to see the evaluation of that refrigerator in form of CU, that is known as the coefficient of performance. So we are going to majorly wound around the second law statement. So second law of thermodynamics is defined in two ways. So there are two vital definitions of second law, and that is your Calvin's Planck statement, and the second is the Clausius statement. We are going to see that in depth. And then you will in depth see the Carnot cycle, which is representing the heat engine, and then you are going to see the reverse Carnot cycle, which is representing your refrigerator. And then we are going to see the principle of Carnot related to the efficiency of a heat engine and irreversible heat engine. And then we are going to define mathematically the COP value, mathematical derivation of that, and then we are going to switch over to the problem. So it is a very fantastic topic of thermodynamics, that is second law, and our first part of the study goes with defining what is a heat source, and then I am going to define what is a heat sink. So heat source. So heat source, basically the word itself says that it is a mass, or it is a body which is having huge amount of heat, and that heat is readily available to get transferred to a particular system, or it can be transferred even to the atmosphere. Now, what is the definition of thermodynamics for heat source? The definition of thermodynamics for a heat source is that if you take out a particular amount of heat from the heat source, then the temperature of this heat source, suppose we are assuming it as TH, so the temperature of the heat source will not drop. Now that is the thermodynamic definition of a heat source. So it has been assumed as a body that irrespective of the amount of the heat extracted from it, the temperature or the heat energy present in it, it never diminishes. So this is a very large body, and it is having enormous amount of heat energy. So with the withdrawal of some heat for practical use, the heat energy inside will never degrade. And the best practical example of a heat source is a sun. Though sun has its diminishing time, it has been assumed by the laws of physics that sun is going to diminish, expand, etc. and so on. But taking into consideration the macroscopic thermodynamics, so for macroscopic thermodynamics, sun is the best example which explains that it is a heat source. Now, similarly, you have to define what is a heat sink. Now, similarly, in the fashion of source, there is an ideal body. You can assume this is an ideal body, and this ideal body is having a temperature of Tc. And you are using this ideal body for your practical application to absorb the heat energy and get into it. So you have a rejection of a heat energy from a particular system, and this heat is going to the heat sink. So when it goes to the heat sink, the temperature of this body should increase. Is it okay? So this temperature of the body should go on increasing, but actually this will not happen. So when this doesn't happen, this makes the definition of this body as heat sink. So what is a heat sink? A heat sink can be defined as an imaginary body which is having two huge mass, such that the temperature of that heat sink remains constant, irrespective of the amount of the heat you add into it. So the practical best example of a heat sink is nothing but a seawater. So a seawater is used as a cooling fluid to cool the condenser coils of many thermal power plant. For example, the Dahanu thermal power plant. In the Dahanu thermal power plant, the steam in the condenser is getting cooled with the use of seawater. Now there are some disadvantages with seawater, that the salt associated with it corrodes, or I mean to say it provides some rust on the surface of a condenser coil. So that has been taken in the service part. That is not a part of our study, but I mean to say that seawater is always available at low temperature for the heat, that is the waste heat that you need to transfer it to the other system. So that is the meaning of a heat sink. That whatever is the amount of the heat transferred in the body, the temperature of that heat sink will not increase. So these are the two ideal concepts that first we need to study before going into the second law. So that is about the heat source and that is about the heat sink. Okay. Now with this understanding, we define what is a heat engine. A very fantastic application of second law of thermodynamics. Okay. Now construction of a heat engine is having too many hardwares, many geometric parameters, many combustion chambers, spark plug, etc. so on. But for studying thermodynamic aspect, we are going to only consider its boundary. So a heat engine thermodynamically is constructed using a hot source. Okay, so this is a hot source. We can also call this as a hot source reservoir. So this hot source reservoir is always at a high temperature. We call that temperature as TH, and this TH will never decrease. Similarly, there is a cold source reservoir. Cold source reservoir. Now this cold source reservoir is maintained at a temperature of TC. T cold, basically we can call it as T cold, and this T cold is such that irrespective of the amount of heat added, the temperature of this reservoir will not change. Now in between this, if you try to construct a machine, such that that machine is absorbing the heat from hot source reservoir, and let us take that the heat which is absorbed is written as QH, for example, and with absorption of this heat, this machine converts some amount of this heat into mechanical work. So some amount of the heat is getting converted into mechanical work, and that we indicated by W. And the rest amount of the heat energy left, that is being rejected directly to the cold source reservoir, and the amount of heat rejected we call it as QC. So this typical machine which is consuming the heat from hot source reservoir, converting the partial of heat absorbed into work done, and the remaining amount of heat is poured into the heat sink. This machine is known as a heat engine, and we indicate it by HE. So thermodynamically, this is the layout of a heat engine. We are going to study its efficiency, COP, etc. so on bit later on. Okay. Now, I have to, apart from this layout diagram, I will define the practical heat engine, one of our practical heat engine. And that practical heat engine, fortunately, it can be a steam power plant. Okay, so what happens in a steam turbine power plant, steam turbine operated power plant? What happens? There is a boiler. Okay, now this there is a boiler, and this boiler is having some water over here, and this water is being heated using the coals. So the coal bed over here is fired, and ultimately it gives the heat, and this heat is supplied to the boiler. So basically we have heat energy that is Q going into the boiler. Now what happens? The boiler is converting this water into the steam. Now not only that steam is a pressurized steam. Not only pressurized, that steam is a superheated steam. So what is coming out from here is a very high pressure steam, and that too its temperature is much above the saturation temperature. So over here at this point you get a pressurized steam, that is the pressure of the steam as P1, and temperature is much greater than its saturation temperature, and it is somewhere in its superheated range. We require more pressure is going high because the temperature is also going high. Is it okay? And we require pressure because this needs to get supplied to a turbine. Is it okay? And the turbine is expected to carry out some work. So this high pressure and high temperature steam, it goes into the turbine, and when it goes into the turbine, let me show the turbine in this fashion, and there is a cooling and there is a rotating fan over here, the blades of the turbine, what we say, and this steam when getting injected in this turbine, it hits the fan and this fan rotates. Is it okay? And what you get out is again some steam, and you get some water vapor also. So based upon this rotation of the fan, you get some mechanical energy as an output, that is W of a shaft. Now this rotating shaft, when so the pressurized steam at temperature much greater than that of the saturation temperature, it enters into the turbine, and the turbine is having cooling is having the blades, and this pressurized steam hits the blade and the blade rotates. Is it okay? So when it is entering the turbine, we show the turbine in this manner as a turbine, and inside this turbine you are having the blades, and the steam is hitting the blade and it is rotating the blade. So what you are getting out is a mechanical shaft work output, and this shaft work when combined with a permanent magnet, when this shaft is rotating in a permanent magnet according to Faraday's second law, you get what is the electricity output. Okay, now ahead what happens here? When the steam is leaving the turbine, it is leaving the turbine at low pressure and low temperature. So it might happen that some amount of the steam may also get converted into vapor, liquid vapor. So over here it is not guaranteed that we have a saturated liquid. For example, if it is a water, we don't have 100% of water over here. It is not usually possible. We have some steam and we have some vapor. It depends upon the type of amount of pressure at outlet and the temperature at outlet. Now what happens that over